Hello, welcome to another problem session. This is an interesting problem where this chain, this is t equal to 0, or t equal to 0, and you're holding and just let go from rest. So it's going to fall, but here at this t equal to 0, barely touching. So you don't, there's no weight of the chain on the pan. So under the pan is a spring. A compression spring is indicated by a indicator, and which gives the reading. The scale is written so that you have divided by G, and so it shows 4 divided whatever force is feels divided by G. So this reading here is the spring force, which is a normal force here on the pan. So we'll call it a normal force. We'll call it a force on the pan upward. Okay, so that's the force we'll feel. The pan will feel from underneath, and we'll say pan's acceleration is 0. Okay, so we the reading is this force divided by G. Okay, that's the reading. Okay, so this is the setup. At some time, at this point, the chain has fallen distance x, and it has some speed v here, and because the chain remains straight, this v is same as this v. Okay, but some of the chain has fallen, so this is the chain amount fallen. That guy's v is 0. That's what it says here. And at this time, we're supposed to figure out what's the reading here. Well, so we're gonna figure out this f at this point. At this point, you can see there's only f here is weight of this pan. So at that instant, at t equal to 0, this f is balancing the weight of the pan. You can think of calling that 0 if you like, but in this problem it doesn't say it's 0, so I'm going to stay with so this will be like little mg, and so the reading here will be, at this instant, reading will be is m, right? Now because in this situation now, when the pan is when the chain is falling, situation is quite different. Okay, so we need to keep track of how much is falling. This whole thing has mass capital M, and the length is L. So, and the distance, we're supposed to carry this much distance, right? So that same amount of distance has fallen here. So let's define mass per unit length so that we can convert that. So let's say lambda is m over L. Just going to define that. Call that m over L is lambda. So this part is lambda x. That's how much is sitting there. So if you look at it force wise, so you have a the force we want to find, and we have the little mg of pan, and then little lambda x g of this thing, and then we have this thing is losing momentum, so this force will be the rate at which momentum is being converted here, right? The rate of momentum change of falling chain, right? So that's so these three this will act like a impulsive force. So this is like an impulsive force. So let's call it Fi. So how do I figure these are easy to find, but how do you figure out Fi? Well, if you look at this particular thing was over here, and from here to here it has fallen a distance x under gravity. This part is free fall. So from there you can say this v has to be equal to square root of 2gx, because originally v was, for this little piece, v was 0, and now it's going with a v. So that's the v. So this is the same as that v. So if I look at a very small piece, say dx, so here is another picture. So over here, this dx, which is has a mass equal lambda dx, and it's falling with a v, and immediately this is before, and then dx mass equal to lambda dv at rest. So that's the momentum change that's taking place in that. And so that will be this mass times that v. So we'll have a v lambda dx, and that's the change in momentum over delta t. So that's the impulse, and that's the change in momentum. So that will give me Fi. Okay, let's so the Fi is v lambda dx over dt, and that's the same as v, because we are looking at this is x coordinate, and so this is inertia. This force, impulsive force, is v lambda v, so that's equal to lambda v square, and v was square root 2gx, so this is 2g lambda x, and lambda x is the mass that has fallen. So combining this and this gives me the force. So the reading, so the force is equal to this mg of the pan, this lambda xg, and this is plus 2 lambda xg. So this is actually 3 times lambda xg. So m plus 3 lambda xg. So the reading in A, the reading is this F divided by G. So that will be F divided by G is m plus 3 lambda x. So lambda you can write down is m over L. So m plus 3 m over L x. This is the answer. Okay. B is what is the reading when the whole chain is formed. This is just a B is when x equals to L. When x equal to L, I have 3 times the mass of the chain. The reading will be is m plus 3 times mass of the chain. Very interesting. The very last one is going very fast. Okay, and it actually so the total will be 3 times the mass of the chain. It's the instant the last bit falls. If you tar the scale, if you set the little m to be 0, if you reset a scale so that reading at t equal to 0 is 0, then you have 3m as your final reading. Okay, yeah, I really like this problem. This is one of my favorite problems. Let's just recap what I did. So first I had to understand exactly what forces will be involved when chain is falling. So this is the most critical figure for me when I'm looking at this problem. For me to come up with this figure was the most critical figure. So I knew I need to get this because I need a reading will be this divided by g. So you have to know how the scale works. And this force is actually balancing these two forces are easy to see, but then this inertial the force from the impulse, sometimes called inertial force, force from impulse on the pan. I had to realize that, and then I went around looking for how to solve it, because I will need how quickly the momentum is changing. And there's a model here which says this is the actual hint that you need to use change in momentum. Okay, so change in momentum means the rate at which velocity and mass is changing around here. And so I looked around this process here, how to get a expression of velocity. So another assumption was this chain remains straight, and so that this whatever I found here is same as over here. And now I converted this v into this, and then the rest is pretty much just algebra. Okay, see you another video. Bye.